Hey guys, so we're going to do 5.2 today, which is all about bisectors in triangles. So we're going to look at perpendicular bisectors in triangles and what happens. Um, and then we're going to look at angle bisectors in triangles and look at what happens. So we have two objectives for today. First objective is to show that the point of concurrency of the perpendicular bisectors in a triangle. So if you draw all three perpendicular bisectors in a triangle, they connect at one point. And it's called the circumcenter, so right here, is equidistant from the vertices, and use this property to solve problems. Then we're going to show that the point of concurrency of the angle bisectors, which is called the incenter, so that's if you draw all three of the angle bisectors in a triangle, they meet at one point called the incenter, is equidistant from the sides, and then use this to solve properties. So we have a lot of new vocabulary in this lesson, right? There's 6 new vocabulary words, and then 2 new theorems. Really, they're postulates, but they're under the theorems and postulates page. So we have a lot of stuff to kind of go over before we can use these ideas to actually solve problems. So let's jump down to our terms page so that we can define this new vocabulary. All right, so here we are at our terms page. And you're probably going to want multi colors on this. There's a lot of detail in these drawings that we're going to do, and I don't do so well drawing on this tablet, so we'll see how well I do, but it might be really helpful to have multicolors going on here. So the first thing that we're going to define is the circumcenter of a triangle. So this is the point where the perpendicular bisectors of a triangle intersect. So I'm going to work real hard here. I'm gonna draw a nice big triangle. I don't like it. I guess it doesn't really matter that much. Okay, so here's my triangle. And I'm going to draw the perpendicular bisector of this triangle, of each line in this triangle. So for example, from A to C, I'm estimating that the center is about right there, and I'm going to draw a line perpendicular, like so. Then for BC, I'm estimating that the center is around here, more or less. And I'm going to draw the line perpendicular. Boom. And then here, the center is about here. Oh, this one's going to be more difficult for me. It is not perpendicular. There we go. Something like that. So that's perpendicular. And so all three of these points, all three of these lines intersect at this point called the circumcenter. And the circumcenter doesn't necessarily have to be inside the triangle. So notice here, it's not inside the triangle. And that's okay. The next term that we have is circumscribed. So this is when a figure touches another at points without cutting the figure. So it's basically drawn around. So what happens, I'm going to draw like a really tiny triangle here. And I can draw a circle around this triangle that doesn't cut through the triangle at all. And so I'm going to go ahead and do that and then show you guys when it's done. So I did the best I could here. So notice that I was able to draw this circle that intersected at the vertices, but it did not break up the triangle or cut the triangle in any way. So this would be a circle that's circumscribed around a triangle. Inscribed is the opposite. So this is a figure that's drawn inside. So if I have a larger triangle here, okay? I can draw a circle that fits snugly inside this triangle, and I'll show you what that looks like. So here's an example of what we call an inscribed circle, right? The circle is inside the triangle snugly, meaning it's as big as it can be without going outside of the triangle. So hopefully that makes sense so far. Let's move on to our next ones. Our last three vocabulary is concurrent lines. So this is just a set of lines that intersect at a single point. So anytime I have a line, and then like another random line, right? And then another random line, right? And it can be two or more lines. But if they intersect at one point, that point is called the point, oops, excuse me. I didn't even know I could do that, of concurrency, which is our vocabulary down here. The point where concurrent lines intersect is the point of concurrency. So anytime that I have like the three perpendicular bisectors, like I had up above, excuse me, so those three lines that intersect is the point of concurrency. Okay, last, I was gonna say we don't really need to draw anything here. So the last one is the incenter of a triangle. And I really want to make these lines as straight as possible. Okay, so we're going to draw a triangle like so. Beautiful. And the incenter is the point where the three angle bisectors of the triangle meet. So if I take this angle, well, I should label it, right? A, B, C. So if I go from vertex B and I split this angle in half, so split it in half so that this angle and this angle are the same. Okay, and I'm going to do the same thing with angle A. I'm going to split it in half so that this angle and this angle are the same. And then same thing with angle C. I'm going to split it in half, more or less, and it should meet here at one point, and that point is called the incenter. It is also a point of concurrency because multiple lines are meeting at one point. Okay, so that's all of the vocabulary for today. What we're going to do now is we're going to look at concurrency of perpendicular bisectors and concurrency of angle bisectors, and we're going to look at the cool things that it does. This is really where you're probably going to want your colors. So let's go down to the theorems and postulates page. So here we go, and we're going to look at concurrency of perpendicular bisectors and the concurrency of angle bisectors. Okay, so let's read this very slowly. It says the perpendicular bisectors of the sides of a triangle, so if I just draw the perpendicular bisectors, are concurrent at a point equidistant from the vertices. It's a really cool feature that happens with perpendicular bisectors in a triangle. So I'm going to try to use lots of colors here. So I'm going to go ahead and pause and get my triangle and everything all set up. All right, so here's my triangle ABC. And what I'm going to do in a different color is I'm going to draw the perpendicular bisectors of this triangle. So again, I'm going to find kind of the middle right around there, and I'm going to draw a line perpendicular, like so. And then I'm going to kind of do the same thing with BC. I would guess that this is kind of the middle. And then I want to draw a line perpendicular. It's really hard when I can't turn the page. It doesn't have to go through the vertex. Okay. And then same thing with BC. I'm guessing that like this is kind of, or sorry, BA. I'm going to draw the perpendicular bisector. Okay, and I'm going to call this point right here point D. Okay, so something very special happens here, and that kind of looks like an O. It's a D. So this point, which is from the perpendicular bisectors, is equidistant to the vertices. So this distance right here from B to D and from C to D and A to D are all the same length. So AD is congruent to BD, which is congruent to CD. So once you found that circumcenter, right, that point that where all of the angle bisectors touch, that point is equidistant to the vertices, which is super cool. The other one is what happens when all the angle bisectors come together. So I'm going to draw, this one I kind of want to draw bigger. Let's do that. Okay, so here's my triangle A, B, and C. Now I'm going to find the incenter where the angle bisectors meet. So I'm going to cut angle B in half and just kind of draw it down. I'm going to cut angle A in half. And I'm going to cut angle C in half. This is the hard one. Going from right to left is not easy. There we go. Okay. And we can call this point again, point D. So it says the angle bisectors of the angles of a triangle right here are concurrent at a point that is equidistant from the sides. So now we have something that's equidistant from the sides. So if I draw a perpendicular line from point D to side AB, let's call this E, and then I do it again. Oops, that's not really that perpendicular. Holy moly. Perpendicular. Let's call that F. And then this perpendicular, let's call it G. All of those green side lengths are the same. So here, ED is congruent to FD, which is congruent to GD. So all of those lengths are also the same. So if I know that they're angle bisectors, I know that the point to the side is going to be the same. If they're perpendicular bisectors, I know that the vertice to the point is going to be the same. So those are the two that we're really going to focus on today, and we're just going to do a few problems on it and just get a little bit of practice before you guys try it on your own. So let's go back to 5.2 so that we can finish our notes. All right, so we're back here at section 5.2, and we're going to look at these examples and see if we can't work through and figure out how to solve them. Okay, so really it's just example 1 here. The best thing that you can do is to fill in all the information that you know. So this says if QP is 3 times x plus 1, okay, and RP is 5x minus 3, what is the radius of the inscribed circle? So remember that the radius is just going to be this distance right here. And all three of these are going to be the same distance because we're bisecting angles. Okay, so since QP and RP and we can call it SP, since all of these are the same length, that tells me that 3 times x plus 1 is the same length as 5x minus 3. And this is something that I can solve. We can distribute this 3. So 3x plus 3 equals 5x minus 3. Let's subtract this 3x. So I get 3 is equal to 2x minus 3. Add 3, add 3. 6 is equal to 2x. I'm going to divide both sides by 2, and I get x equals 3. And that's great. X is 3, but it wants to know what is the distance from this point P to the outside. So I'm going to have to plug it back in. So I'm just going to use RP. You could have used QP as well. But RP is 5x minus 3. So 5 times x, well, 5 times 3 minus 3 is 15 minus 3, which is 12. So the radius of that inscribed circle is 12 units. So just to show you what we mean here, if I were to draw a circle, probably very poorly because you guys have seen me draw before, right? Something like this, more or less, right? Here's the center of the circle, and then the radius of the circle is going to be 12 units. So that's what it was asking me to find. We have 3 triads here, but I do want to go through one of them with you. So let's do A together. So again, the biggest thing that you can do, and I'm actually going to probably zoom in, the biggest thing that you can do to help you is to fill in all of your missing information, fill in what you're given. So here I'm told that the measure of angle BAF is 15. So from B to A to F. So that tells me this right here is 15. Well, if that's 15, since this is an angle bisector, I know that this one is also 15 because it's cutting the angle in half. So both of those angles are the same. Then I'm told that CBF, so from C to B to F, so this angle right here is 52. And again, if that angle is 52, then this angle is also 52. And then it's saying, what is the measure of A to C to F? So this guy right here. What is that angle? So if I look, and I'm just going to quickly draw this triangle in a different way, angle A is made up of 15 and 15. So angle A is really 30 degrees. Okay. Angle B is made up of 52 degrees and then another 52 degrees. So this is 104 degrees. So I'm curious, what is angle C? Well, I know that the 3 angles of a triangle add to 180. So if I call this X, right, I know that 30 plus 104 plus X equals 180 degrees because the angles of a triangle add to 180. So this gets me 134 plus X equals 180. I'm going to subtract 134 to both sides, which gets me x is equal to 46. So that's great. That tells me that angle C, all of angle C, is 46 degrees. However, if we look back at our main drawing, I just want to know what half of angle C is. Right? I don't want the whole thing. I just want half of it. So I'm going to take my 46 and I'm going to divide it by 2, which tells me that this is 23 and this guy is 23. So the measure of angle ACF is equal to 23 degrees. So as usual, once you've solved, you need to ask yourself, is that what the question is asking me to solve? Okay, so you guys, there's 2 U-tries here. I want you to try both of them. So you're going to pause the video and try them. And then when you're ready to go over them, you can go ahead and hit play and we'll review it. All right, so let's look at part B here. And again, I'm going to fill in the information I know. I'm given that EF is 3y minus 5. And I'm given that DF is 2y plus 4. And it wants to know what is the distance from F to AB. So again, right, keeping in mind that that distance always has to be perpendicular. And let's call this like G or something, right? So it wants us to find what is FG. So I know that EF and DF and GF are all the same length because these are all angle bisectors. So since I know that they're all the same length, I can say that 3y minus 5 has to be the same as 2y plus 4. Has to be the same length. So I'm going to solve for y, so it's minus 2y, which gets me y minus 5 is equal to 4. I'm going to add 5, and I get y is equal to 9. Is that what it's asking me to find? No, right? It wants me to find the distance from F to G. Well, the distance from F to G is the same as the distance from D to F or from E to F, right? They're all the same. So I'm going to take the distance from D to F and I'm going to solve for that. So that's 2y plus 4. And that, I know what y is. Y is 9 plus 4. So 2 times 9 is 18 plus 4, which is 22 units. So if the distance from D to F is 22, then that means that the distance from G to F, I wrote it backwards, sorry, from G to F is also 22. And also E to F. But specifically, it wanted me to find GF here. So it's 22 units. So hopefully that kind of makes sense on how we were able to get that. The last one we're going to look at, I know it's zoomed in really far, I just wanted to be able to draw on the diagrams. The last one tells me that the measure of angle JLP, so from J to L to P, so this guy right here, is 30 degrees. So if that's 30, then that tells me that this is also 30. And that the measure JKL, so this whole thing, is 74. So again, this whole angle K is 74. So if I divide that in 2, that tells me that this angle is 37 and this angle is 37, right? Because that adds up to 74. And then the question is, what is the measure of P? So where am I? P to J to L. So I'm looking for this guy right here. So again, if I draw this triangle out, and here's L, K is 74, L is 60, right? Because 30 and 30. So I want to find this guy, J. What is J? So we can do 74 plus 60. Oops, excuse me. Plus X equals 180. Okay, 60 and 60, 120, 134. So this is 134 plus X equals 180. Subtract 134 to both sides. And I get X is equal to 46. So right here, angle J is 46 degrees. But I specifically want half of angle J, right? Are we with me? Hopefully, okay. I specifically want half of angle J. So I'm going to take my 42 and I'm going to divide it in half. So I get the measure of angle, PJL, and half of 46 is 23. Now I know that that was the same answer as up above. It is not always 23. This is just weird examples that ended up with the same answer. Okay, but the measure of angle PJL is 23 degrees. That is it for lesson 5.2, just the one example and the couple try-its. Please, 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 if you need help on any of this, if you want me to explain it again in person, we can go over it in person, on Zoom, whatever you need. But we want to make sure that we're feeling okay about this. And I know that it's a little bit more complicated and there's a lot of vocabulary going on. So if you need any help, just make sure that you reach out and get the help that you need. Otherwise, that's it for 5.2, and we'll see you soon.